So we'll start with looking at how to classify or segment magnetospheric data into different regions. And why do we want to do this? Well, there is a lot of data. If you have a lot of data from your satellite, which we have, it's you want to have an idea on where to start looking for stuff. Where, if you're interested in looking at events in the solar wind, you want to look at solar wind data. If you want to look at the region crossings or the bow shock, you want to look where the solar wind is crossing the bow shock. So you want to be able to distinguish or categorize these as a way to start looking at, start figuring out where to look for data instead of just having a quick look at or going through all of the data by hand, basically. Now, for MMS case, there is a lot of labels from scientists or the scientists in the loop that actually took a look at the data before they downloaded it. So here there is some kind of labels, and there has been a lot of work throughout the years to actually classify all of this data for using machine learning. Now I should have had those, but the one is work later on after using the work from Olszewski, using neural networks to classify a lot of the 8 years of MMS data, and later work by Paul Edens actually used Gaussian mixture models to classify all of the data using a more unsupervised method. So there are some work on this already, so that's quite interesting to look at. But it's also a great way to start to have a look at machine learning and classification. And what we actually want to find methods for doing here is teach a computer to do some semblance or of what a scientist can do by simply looking at the data, not simply looking at it, but looking at the data. So the general pipeline that we'll have is first you create your data set. That's what we did in the last session. Then you do some feature engineering. Here you actually take the raw data from your data set and create the features for your model. Either, as we saw before, the raw data, or you start looking at actually using some derived feature. Then you can do some transformation on these. For machine learning models, it's quite important the relative scales. As in general, if you have one feature that has a very large values and have a quite large range, the models tend to look at these features more closely, because they have a larger variation in the values. So you might need to scale features differently to get them in a similar range. Then we train our models. Can be neural networks. We look at some clustering methods to begin with, and then we evaluate our models. We heard yesterday about the importance of using different data sets or dividing our data set into different categories. So testing, training, validation, and testing. This is especially important if you have labels, so you have label data where you actually have something to verify against. And throughout this lecture and the exercises this afternoon, you look at different areas where you might or might not want to actually divide your data set, and why you don't want to divide it in some cases. But we'll start to look at or continue to look at knowing our data set a bit more. I think I try to go quickly through this slide because don't have very much time and want to have a lunch also. But knowing our data set, we had a look at the four dion spectrum, and here we have divided it into our different labels and 10 minutes time range. So we can get a feel for how the different regions actually look. And many of you are working with space physics, so you have probably seen this or similar plots already. And so for this afternoon, here we have divided in distinct separate time windows where we have continuous of the same label, basically. So the labels are for each time slice, but we've subdivided them into consecutive windows. And for this afternoon, we have provided a quite nice data set or a data set class that in Python that does that for you. So from the space5ml, you can import data set, spectrum data set, and then you can simply specify how many samples you want your size window. And it will give you a clean data set with only labeled data, not unlabeled data. There is some options to get some unlabeled data in there also. But this is the data set we look at. So a window of a time from a spectrum. Of course, there is a trade-off here. If we have longer time windows, we have more time. We have more data to our models, larger feature space, because our entire feature is all our time or our energy beams and for each time slice. So it's basically 32 times our number of time steps. To have more data for a model to look at, but the longer time windows we have, the fewer data samples we get, as we have a limited time. Our data set is limited in time, so then we have sort of less data in another sense to give to our model. They can have more information in each sample, but less different samples to look at. But we can also notice one thing here. It's that while it's high dimensional, there is quite a few. It's not very varied along the time axis. The magnetosphere is quite similar along the time axis. So it's a magnetic sheet, the solar wind. Ion force is a bit more time dependent here. But this very clean data set has a quite high degree of regularity. So we can actually look at using PCA or some other feature reduction technique to actually reduce the number of dimensions or the number of features we have. But before that, we also have to look at the class imbalance. So I noted at the end of the last lecture that we have a class imbalance in our data set, a lot of solar wind data. And here I've removed the unlabeled data also, so now we only have clean sample. Now, what's the issue with having a class imbalance, especially when we try to do a supervised data or supervised learning, is that the model will tend to look at learn the higher or the classes with larger number of samples. For example, here the solar wind and the magnetosheet comprises 70% of the data set. So if the model is just very good at distinguishing between those two regions, it will have a great accuracy, but it might perform extremely poorly at telling if you have an ion force shock or magnetosphere. And in some cases, that's what we want. It might be what we want, then it's fine. But in general, we want a model that generalizes it as much as possible. So we have two ways of fixing this. Either we can downsample our logic classes to our minor classes. Then we discard data, which it's not really something we want, but there might be what we have to do. We can also upscale data, so we could either sample the minority classes multiple times, or even in some cases you could try to interpolate the data for these minority classes. So try to basically create new data, create synthetic data. But if you upsample data, we instead have the con that we don't actually have more four-stroke data. We only have more of the same samples. But here, and the dataset class I provided also have the capability of downsampling. I meant to actually give you some code for how you could do this by yourself. It's quite easy to resample based on the indexes for the labels. If you use sklearn or scikit-learn, or even PyTorch have that capability. But yeah, so here you can simply resample to how many samples you want for each data.
Yeah. I'm sorry for the question. If you downsample the SolarWind and Magnetospheric case, so in this case, your model will be poor in all four cases, right? Or it will be equally good in all four cases. Yeah. It's like when you discard data, you will have maybe more poor representation, worse results for SolarWind and Magnetospheric, and the same results for Iron Forge and Magnetosphere, or not?
Yeah, that depends on your data and your model. So in this case, the data is very nice, maybe too nice to some extent. So this if you look at two different samples in SolarWind, they will be quite similar to each other. But so in this case, I would say will perform equally well on all cases. But what can happen if you downsample this and you have a SolarWind or a category here that's very varied. It can be that in best case you have a nice, good representation of all the data here, but you might have actually two subgroups in this data where one group has a certain feature that looks in a certain way, and the other group doesn't have that feature, but it's still the same group. And you only sample all of or most from one group. Then it's very likely that you will perform very poorly when you then go back to this group. So what you can do to sort of mitigate this is that you can subsample for your training, but then you will check all of your data. Let's say like you take a subsample of all your data for training and train on that, and then you look at what data did I not use for training, not just what data did I split into my test set, but also what data did I not use for any data sets. And then you look at those specifically and test how well you perform on those. Then, however, and that's, I would say, very good practice, but you also have to be careful with what metric you use then. We'll look at the metrics once again later on here, but if you remember from yesterday, Federica talked about accuracy and precision and recall, and those all show you different things. And you can have situations, and I don't have a good example right in my head, but you can have situations where you have a very good accuracy because you're have very few false positives. Or you have a very good accuracy, so overall it looks very good, but you might have very many false positives, and then you have a very poor precision. And that's because you have or that could be because you have an imbalanced data sets when you actually in your when you do run your metrics. But absolutely, if you subsample, you are tossing away data, so you are at risk at not using data that is vital to what you're actually looking at. And again, this afternoon, the first part where you will, or first the part where you do uncluster or unsupervised machine learning, you will actually look at doing all these steps that you know, but for an unlabeled data set where you don't know how many clusters you have, or you know based on the region the data is from what you would expect, but you will try to evaluate how many clusters, how many regions that the actual machine learning method thinks is there, and then try to look at those. Yeah.
Well, yeah, that's good.
Yeah. But so class imbalance, especially in training, is very important when you train labeled or supervised models. Unsupervised model is less important, but it will also affect your model basically. And yeah, another part that I discussed briefly before was scaling. So if we look at this ion distribution here again, we can see that the magnetosheet ion foreshock and solar wind has flux levels that are on level of 10 to the power of 8 here, while the magnetosphere is almost 2 orders of magnitude lower. And if we use, which we'll later on use, for example, PCA, which finds the axis of highest variance, the values where, or the features where you have the highest values will have a disproportional, be a larger part of the model, basically. So you need to scale your data to allow your model to find the features, to find the connections that you're after. And what you often see is in machine learning courses and machine learning when you start it, is that you use some standard scaler, or min-max scaling. So you take and calculate for each feature the minimum and maximum value, or the mean and standard deviation, and then you use those to scale that feature. And that's quite good if you have like different features, like if you have the magnetic field and the ion density. They're not, well, they are connected, but they're not, let's say, directly connected. But if we look at the ion spectrum here, you have a quite direct connection between one energy beam and the next energy beam. So, and in our feature here, or in our window here, each pixel is a feature. So if we would scale it like you standardly or usually do in machine learning, you will end up with all these values at the bottom here has a much higher variance, or higher part of the total variance than is actually meaningful for your model. Because if you look at this, you see a lot of the differences is not actually at the lowest energy levels here, but on the higher ones. So it's not just take this scaling and apply it. You also need to think about which is the most appropriate scaling. And in general, you want your feature values to be around 1. or closer to 0 and 1 range. But you can have them higher. And in this case, we'll look at simply using a log 10. We'll add a 1 to our variable, so we have some values here, which is 0. So take our flux and add 1 and then take log 10. So we can scale it down that way. We'll also look at the min-max scaling, so simply scaling all features between min and max, and then we'll see what happens, what the difference is. Yeah. So if we do the scaling and then apply a PCA, a principal component analysis, we get a number of features with each feature has decreasing variance. Then we can also plot a street plot or which plots how much variance each feature contains, or how much of the data variance each feature explains, I should say. And we can also plot the cumulative variance, so we can see how much of the total variance in the data we have explained when we have a number of reduced features. And here we do this for log 10 and max min scaling. And we can see that at around 8 to 10 components, I wrote 5 to 8 there, but around 8 to 10, we're starting to have as much explained variance as we can get into the components. For the log scaling, where we have just explained about 65% of the total variance here, but all of the adding components add extremely little more variance to the actual data, and we will have to move up to like at the end before we actually get to 100%. So clearly, we can do a lot with just rescaling or the number of features to about 8 or 10. Yeah. So if we then rescale it or transform our features to a reduced feature space based on our PCA, we can plot our clusters or plot our data samples and color based on our labels. So to the right here, you see the log 10, and to right the min-max. And I think this is interesting because here you can clearly see that the magnetosphere in a min-max scaling it's only more or less a single point. So it's not actually, it doesn't contribute much to the variance. It's very singular, while the rest of the regions are more spread out. And you can see some cluster corresponding to the magnetosheet, but it's for these first 3 components, the solar wind and iron foreshock is spread around it a lot, and to some extent you can often see sort of a symmetry in some sense around the 0 value for at least the second and third component for the solar wind and iron foreshock. But if we look at the log 10 scaling instead, you have much more distinct clusters for the different regions. So for this specific case, for this feature, it would seem that the log 10 is the most appropriate, because we can see difference in clusters. The computer should also be able to find difference in clusters. I should say though that it's if you use min-max scaling, it becomes very good at finding that magnetosphere. Also, I'm not going to go more into this, so much into this, but the interesting part with using PCA is that you can look at the components, the principal components it finds to use for the vector for the transform down to your reduced feature space. And here I have technically they are flat, but you can reshape them into your spectrum shape, and you can start to look at what parts of the spectrum that the model is actually looking at, and we can start compare the differences between the min-max and the log scaling. And we see quite quickly how the min-max scaling is very focused on this area where you have this solar wind beam and area around where the magnetosheet has its highest flux, while the log scaling is much more focused on the rest, because around just the center of the solar wind beam, it's very it's not that much variance in because three of the categories have very similar values on those energy levels.
Oh, I have a question. What's the label of the color bar? It says loading.
Yes, I would mean the units of it. Or I don't know what it says loading.
Okay, it's from your laptop, or did you write loading over there?
No, I wrote loading.
Or maybe it is typo.
What?
It auto-corrected.
Yeah, I mean, I hate making these spectrum plots. So the plotting code is AI generated. So yeah.
Okay, makes sense now.
Yes, but you can start to understand what the model is. And the color bar here, it doesn't, I guess you technically have a unit on it, but it represents how much each pixel influence the feature value, so to say. So yeah. Oh, yeah. Short summary. I don't. We'll go quickly on to the unsupervised classification or clustering. And I forgot to tell you before also, but each lecture part, so the first on data creation, the second on first look at data, and then this section and the following section all has a notebook in the GitHub repository, which I have linked on the website, which contains most of the code to create all of the plots in this. Yes. So what's clustering for? Well, basically to find correlations between data samples without actually having to find define labels and train a model supervised. So you can use it as a tool to group together data that is similar, either on raw features, or as we did here, we did a feature reduction and then clustered on those features. And that feature reduction can be a PCA, very simple. It can be other linear, basic, traditional machine learning techniques, or it can also be more advanced techniques such as autoencoders that try to create a reduced feature space, which you then can operate on. But as it's not supervised, our clusters is arbitrary. So we need to actually have a way of interpreting them. Stefano mentioned before how you can then go back to physics and look at the actual data and based on your knowledge of the interpret what different cluster means. In this case, we have labels which we can compare to as a sort of baseline. But before that, one of the core things doing our train and test split In this case, I do a train and test. I don't do a train validation and test because I'm not doing any hyperparameter tuning. I train my model for a specific number of clusters, which is 4, and then I use test set to test how good it actually performs on this. A critical part here is that you always do all of your determination of scaling. If you have a sort of fit the general scaler like for each feature, or you do a PCA here, and then train your model, all of that is done on the training set. You don't do it on your validation or a test set, because then you start to have data leakage, where your test set will actually affect or can affect how well your model performs or how well it learns. And then it might actually perform very well on the test set just because that data was already included in the training in some way. So that's very important. So you fit your scalings, your PCA, your models to your training set, and then you use the same trained fitted scalars and models to actually test on your test set. So to the right here, you can see an easy way using train test split functionality from scikit-learn. One thing also to notice here, if you have a very large data set, very thousands of samples, you can usually do just a random split, and your class balance should be generally preserved. You might have some small fluctuations up and down, but it shouldn't matter. But if you have a smaller test set or a small data set, you might want to use a stratified split. Basically, it subdivides your data set into your different categories or different labels, and then split these equally, then gives you this combined split into 2 different data sets. This will ensure that both your training test and your training set and your test set are split or have a class balance between them. So you're not in your split introducing new class imbalances. Then we have split our data set, our spectrum data set, into training and test. We then transform it using the log 10 scaling, because we had the quite visible separation in our clusters in our first 2 components already. Then so we fit the PCA to our training set, and this should say NPCs here. It says none, but so when we say that we want 8 principal components, we should at least. Here we use all. Now I need to recheck the notebook. But anyway, so we fit to the training set and then transform the test set using this fit. Then the idea here is that we can do all our clustering on our reduced feature space, which instead of fitting on thousands of features, we do our clustering on 8 features, which is much faster. And we should have all the information or most of the information already there. Here we look at 3 different algorithms. Firstly, the basic k-means. You probably or hopefully have encountered k-means in some sense already. Basically, you put a mass centrum in your feature space, calculate the Euclidean distance for all points, then assign all your sample points to the nearest cluster center, and then recalculate where the cluster center should be based on the samples that are assigned to it. And if you do that a number of times, these find a stable spot and you have your clustering. Some of the negatives here is firstly that you have a hard assignment. it's assigned to one cluster only, even if it's like just at the border in two clusters. There are some differences or alternatives where you have a sort of soft assignment based on distance to the cluster center also. But the basics is hard assignments. And it can be quite dependent on initial distribution of the cluster center. So 2 runs with 2 different distributions of where the cluster centers are set from the initial start can result in 2 different distribution of clusters, basically. Not even just cluster indexes, so if one is cluster 0 and cluster 1, but actual samples that belong to the same cluster. So what you generally do is that you run a number of different k-means, and then you take the one that is most or appear most often, basically. And then so you fit your k-means, and then you can predict your labels on your test set. Then we also have a Gaussian mixture model, which gives, instead of trying to fit one center point, it tries to fit a Gaussian. So now you have a more probabilistic assignment, and if you do you can even do a full use the full covariance matrix. So you're not only limited to circular clusters, but they can be elongated along one axis or another. And you get more of a probabilistic assignment, so you can see that in transition region there is a probability that the sample list belongs to one cluster or another instead of a hard assignment. Then also as a alternative, also I've used agglomerative clustering. I don't know if you have used that before. This is in contrast to k-means and GMM. You can't use this to create a model to based on data then predict the next set of data. So here we have sort of cheated and put both our test and training set together, done our clustering, and then we just evaluate it on a test set. But agglomerative clustering works a bit differently. This is only to sort of, if you have a set of set data, if you have a number of samples, you can use this to sort of subdivide it, this set of samples. And what it does is it finds 2 samples which has the closest distance to each other, and then it connects these into a super sample, basically putting the mass centrum in between these 2, and saying this is a new sample, and then it finds of all the samples next to it, which is closest to each other, and then connects those. So it creates a tree structure upwards, where we're always connecting the two samples that are closest, and then if you want k number of clusters, you just go upwards in that tree until you only have k number of super samples, so to say. And that can be a way of do a clustering where you always group 2 samples together which are close to each other, but only for understanding your entire data set, not actually doing any prediction of future samples. These clustering methods are label free, so we don't have any enforced labels. We can't say that cluster 0 is always solar wind. We need some way of actually comparing these without knowing which cluster is which region. 2 of these ways can be to use either adjusted random, or to use both, actually best, adjusted random index or adjusted mutual information. Adjusted random index tries to give a measure on how well 2 clusters agree with each other. So if we have labels in this case, we can use it to measure how well the clustering algorithm clusters together labels of this same label into one cluster. But you can also use it to compare two clustering algorithms and say how well do these two algorithms cluster together the same samples in the same cluster. That works well if you have approximately the same number of clusters that in both that you try to compare. So in our case, the approximate number of clusters to labels. However, if you have more clusters than labels, it's not as good. Instead, you can look at the adjusted mutual information, which tries to tell you like how, if you know which cluster you have, how certain can you be that is part of a certain label. So this can say like if you have you have either cluster 1 or 2, how certain can you be that it is in the solar wind? So this handles multiple clusters better, or imbalanced cluster sets better. But it also have a bias. So if you have very many clusters, it gets more closer to 1. So if you cluster if you have a very many number of clusters, it's much easier to say that if I know that I have this very small subgroup of samples, that this should be in one region. The adjusted part of the mutual information should adjust for that, but it still has a sort of bias towards that. If we look at our clusterings on our PCAs, and there is a risk now here that I have actually done the clustering on the entire PCA, so I have not actually used any feature reduction at all. Double check that, but it looks quite good. It's quite high values, quite close to 1, especially for the GMM, and our two indexes agree quite well with each other. I would expect so, because we have clustered with 4 clusters, which is the same number of labels we are comparing with. So I would be surprised if these two didn't agree quite well. Another way of comparing labels is a confusion matrix. Especially important if you do multi-label classification, and if you use supervised classification. This basically gives you a measurement how well your algorithm puts the correct labels on something, and you can also see where what confuses it the most. And as we have an unlabeled or unsupervised method here, we actually need a way to assign our labels or cluster to labels. Here we have the most easiest possible majority vote. So if majority of cluster 0 is in the solar wind, we say that the cluster 0 is 0 solar wind. There is a better algorithm for this. In the notebook, there is an algorithm called the Hungarian algorithm, which supposedly should be the most optimal assignment. In our case, with 4 clusters, you get the same for both. But if we assign our labels to our cluster to labels, we can do a confusion matrix here. And if we start by looking at sort of the k-means first, we can see that so this is row normalized. This means that of all the true values that is magnetosphere, 91% or 91% of the values is assigned to the cluster magnetosphere, but 9% is assigned to iron 4 shock. So you can see that K-means has a tendency to confuse stuff with solar wind and iron foreshock. So it assigns magnetosphere and magnetosheet to iron foreshock and solar wind. And in the solar wind and iron foreshock, it assigns to each other there. Agglomerative clustering performs better, and the best was the GMM, and here you have very good accuracy on actually predicting magnetosheet and magnetosphere. It still has some confusion with solar wind, and the solar wind it tends to confuse with iron foreshock. And we can also look at this clustered in our PCA space. So here is our ground truth and K-means agglomerative and GMM. And I mean, you can see here then where it starts to confuse samples. Here in this region here, you have a quite overlap between solar wind and iron foreshock. Yeah, that gets confusing. On the other hand, also remember that we have at least 6 more dimensions that it's trying to actually separate them in. So while they seem to overlap here in the third PC, it might not actually overlap. And that could also possibly explain why these down here is assigned to solar wind, but the ground truth say that they are magnetosheet. So in this case also we have a labeled the very clean data set. So all of these labels should be quite accurate. But if you do this on a less than clean data set or even an unlabeled data set, it's often that these outliers or these transitions between different clusters where you can find a lot of interesting events and interesting data to look at. Yeah.
Just question if you remember for the iron foreshock sampling.
Yeah.
Were they really continuously purely iron foreshock without a break of solar wind? Because I think those could factor into the confusion.
Yeah.
Training.
Yeah. So in this, it should be, unless I did some wrong in the coding, but it should be. There is, I did, to add some variation to it, I also added some unknown data. So up to 25% of the sample in one window could be what's labeled as unknown data.
Okay.
And this is also sort of highlights one problem now with using someone else's labels. I've used labels from Olszewski. I have looked at part of it and looked at, oh, this looks good. I think this is more or less correct. But I've not looked at all labels. It's like 80,000 labels. So it's very possible that there is some mislabeled data in there. And so, yeah, especially solar wind and iron foreshock. So, and I mean that can also be a way of using this as when you have labeled data without actually the clustering, but you have labeled data doing looking at it in a reduced feature space and see that here we have overlap, and then you can, instead of looking at these samples and see why are they overlapping, or here you have an iron foreshock actually in the middle of magnetosheet, but you could look at that specific sample and say, okay, why is that located here? Could it be that it's mislabeled or something like that? So also summary here, split your training data, split your data, training, test, validation. Do feature reduction if you have a lot of features. In the notebooks this afternoon, you will not look at the labeled region, you look at unlabeled to do some classification there. then you can also then you can also, if you have different features, look at correlation between features. So a feature reduction might not necessarily be a PCA, but you can also look at, okay, how well does two features correlate with each other, and if you have a value that's close to 1 or close to -1, you might actually say that this feature doesn't add any new information, and you can remove that feature. So I think we'll very quickly go through supervised classification, and I'll try to get it in 15 minutes so we can go to lunch. So supervised classification, here we'll use the CNN. This afternoon you will also try more simple MLP or just standard feed-forward neural network. So the difference from clustering to neural networks, or more specifically, when you go towards more supervised method, is that you're actually trying to optimize for what you're after. So in this case, we'll optimize towards predicting the labels. This does not necessarily mean that these labels are true. They can be completely wrong, but the model will still try to find a correlation between the data and the labels you want. So this is both a strength because it gives you something that predicts what you're after, but it's also a weakness because if you have bad labels, it will probably not find a correlation, or you have a poor accuracy. So it puts a lot of weight on the actual labels that you have and where that they actually represent what you're after. In classification, you can also technically use it to like find a function. Of course, if you do regression, so find a function that takes your input data and gives you your output data, and then it's a question if is the relationship that you think are there is it there or not. So as I said before, we look at the CNN, which is a convolutional neural network. You can have fully convolutional neural networks which has only convolutional layers, but in our case here we'll use convolutional neural network with first a number of convolutional layers which performs convolution over your input data. So in this case, it will, depending on how you look at it, the full spectrum, the full image is the feature for the convolutional layer to go over. And then we have a fully connected layer after that, which takes the output from the convolutional layers, the features that the convolution sees, and try to find the correlation between these features and your classification. So you have firstly a convolution layer and then a classifier layer. And here, this is done with PyTorch, and here I have a mistake actually. In PyTorch, when you do your training, you don't put the softmax on the end. Or depending on your loss function. But a softmax, which is the activation function I have here at the end, tries to or calculates basically the distribution between your outputs. So tries to make so that your outputs all sum to 1. So you basically have a probability that it is class 1, class 2, class 3, and class 4. And in PyTorch, many of the, or at least some of the loss functions you use for training this is built in the actual loss function. So you don't need it here. But you will probably want it when you do classification. It doesn't change the values it gives out, but it gives another way of looking at it. interpreting it. Yes, and then we have our between layers, we have our nonlinear activation functions. In this case, we have used ReLU, one of our most basics to some extent. You saw how that looked yesterday. This is the sort of key neural networks. What makes it that our linear layers doesn't all just collapse to one linear layer to linear regression. Yes, that's the real activation function. Softmax gives classification probabilities. But before we actually give our network or train our network on a data set, we once again need to split our data set. Here, I've used sort of a weird split 60-10 or 30. This is just in this case, so to keep the test set the same size as for the clustering part. So otherwise, I think it gives a weird representation of it. Otherwise, I would recommend that you use 70, 15, 15 if you use validation sets. And the validation set is basically used to see for tuning our network to see that we don't overfit to our training data to look at different network configurations, some hyperparameter tuning, and possibly stopping the network early before the validations loss start to increase. It's there to keep you from adding information from your test set into your training, basically. Unfortunately, Torch doesn't have a stratifying split, so in this case, we use the scikit-learn utility to actually split our test set, our data set into test, validation, and training. And then we'll use a class from PyTorch to create three subsets based on our initial data set and the indexes where we actually have our data. So this is just to create data sets that PyTorch can handle, and then we create data loaders. These data loaders allow us to easily loop over our data, and we can also do sub-batching. So instead of giving the network all of our thousands of samples, we give it a subset of samples. And especially if you use shuffling, so between each epoch, it reorders the samples and how it gives it to the data. This is a way of sort of regularizing, so we keep the network from overfitting to your test set. To some extent, this is so often done now, so it's just how you do it. Often you have also, if you start to see overfitting, you have a lot of other tools that you will be able to use also. Oh yeah. Do this one manually. So training our data, training our network. We have two more parts we want. We have our loss function. In this case, we'll use cross-entropy loss. Quite common when in classification tasks, especially when you want the probability, like in our case. So it tries to minimize the distance between probability distributions. On one side, what the network gives, and other side, what the label says. And the labels is basically a probability distribution with one for the label we want. We have the optimizer also. The arrow's a bit off here, but the optimizer is here. And we use the add-on optimizer. It's a good start, a good place to start. We need to give the optimizer the link or where to find our model parameters. and then sadly the learning rate, how large of a step it should take each iteration when trying to find the best parameters. For the training loop, we iterate over each mini batch of our data set. And here, as we have using a data loader, it's quite easy to just do a for loop with our over our data loader, and it will give us our input values and our output values from the spectrum dataset. So the spectrum datasets have done this split. So here is our spectrum, and here is our batch data. No, sorry, our label. There is some small some steps here. So in PyTorch, this is quite manual. How you do your training in comparison to how you do it in TensorFlow. But I think I like this because it's quite you get to see the steps you're actually performing. So the first step is loading your data, as I said, but then you also have to move this to the device. And this, if you're using a CPU only, no problem. It's all run on a CPU. But if you have a GPU available, you can set this to the GPU, and it will move the data to the GPU and do the training there. And if you see up here, it's shaded, but we have a one-liner here, which basically check if we have a CUDA device, and in this case, it checks for an NVIDIA GPU. I'm unsure if it works for AMDs exactly the same. I've only ever run it on CUDA devices or NVIDIA devices, but this basically tells it if there is a GPU present, use the GPU. And you also need to move the model to the device also before you start. You can, if you forget to move something, it will start complaining that you're trying to compare data which is on the CPU with data that's on the GPU. So it's quite obvious when that happens. Then you reset the gradients, so set them to 0. You run a forward pass through your model to get your predictions. You calculate the loss based on your loss function. Then you, based on this loss, you do a backward pass. This calculates the gradients and adds gradient information to each of your parameters. And then you use the optimizer to actually step through the parameters and update them one step towards the optimal value. Then you also have a part at the end here where it's not technically part of the training, but we store the loss from our training so we can evaluate how well it trains later on. So we add up the loss for each mini batch and then append it to a list. The testing here, I've done the same mistake here. This should say validation here. This should be run on the validation set, not the test set. It is correct in the notebook. It more or less goes through the same steps, but we do it without gradients. So you don't calculate the gradients when you write on the test set. We don't do any backwards pass on it. You don't update the weights based on the validation set. The idea here is simply to look at how the loss or the error on the validation set changes as you train. So you load data, run through your model and calculate loss, and not actually update without gradients and no backward step. So one of the major failure modes for an ML model is as here, and that's true, but now we're looking at neural network specifically, is that it overfits the data or underfits the data. And we saw yesterday how if you underfit, once again, I should say validation, not test, if you underfit, your loss doesn't decrease perfectly. Training and validation sets follow each other. You have a good training, and if you overfit, you might have that the training set reduces, but not the validation set loss. But you can also have that the validation loss follows training for quite some time, and then after a while it starts to increase, and then you can try to stop before it's increased, and then you have sort of early stopping instead to handle overfitting instead of any other method. In our case, it's quite simple data, so we don't have any real overfitting. It's quite nice training overall. Yes, we went through this accuracy alternative metrics yesterday, so we'll not go through them here, but this is a update of them. For our network here, if you look at it, you have quite a good accuracy and prediction recall F1 score for our data, and it looks extremely nice. Very good, right? But it looks very good, but we have to realize that we have very small data set here. I have a very small data set. It's very clean. So here we haven't really introduced any unknown data, and I mean unknown data would not fit into the confusion matrix at all. It wouldn't fit into the precision recall accuracy. You could, because then you could say that if it's to be labeled and is unknown, it is wrong. Yes.
When you see those results, how can you be sure that it's not overfitted or underfitted in the confusion matrix, even though the data is small?
Because this is on the test set.
Ah, okay.
So this is data. This is on data that wasn't used in training. So if you have selected those sets well, if there are good distribution of all the sample, this should show you that your model is not overfitting, basically. In this case, I'm a bit cautious here because the training set is so small. A more accurate way of actually evaluating this would be to include unknown sample and then add so you get this probability out from the network, then add some kind of logic there also. So if it's like 70-60 between, or no, it can't be 70-60. If it's like you have one that is 60% solar wind and like 40%, or let's say 35% ion foreshock, the network might not actually know what it is, and then say put a limit there. Okay, now we say that it's an unknown, and then run that for more data. I think that would be a more accurate evaluation of what it actually does. Yeah. But this is also a sort of a caution, because you do create a clean data set because that's what you want to have when you train it. But then if you have a too clean data set, it might perform extremely well, but when you actually try to use it on real world data, it will have a very high number of false positives, for example. So this is like the first step. I think we have a model that looks good. Then you need to take the next step and look at how it classifies data that's unknown from the beginning. As a small comparison between the two, on our data, this performs much better than, for example, the GMM. But you can also see that this has at least 10 times more parameters in the model, while this has a lot fewer. But this also performs quite well at just distinguishing between basically the magnetosphere or a solar wind iron foreshore. So just because this is a better model, it's not necessarily the model you want. If you're only like interested in finding the bow shock, this might be just enough for you, because it will you can use this to find the transition you're after, basically. I have some key takeaways, but I think we'll go for lunch. One key thing this afternoon will be in Lindsensvägen 3, which is down here. We're up here right now, so go from here. You can go up in here. I mean, I think the address was in the mail I sent out. But Lindsensvägen 3, floor 5. I'll try to see to it that everything is open, or at least someone is there to open it up. Okay, then it's lunch.
What time?
Oh yeah. Let's do, so there's one at 14, so 2 o'clock.
You take our stuff with us, or?
Yes. So we don't have the food more, so we need to bring it to the next location.